Given a finite-dimensional real vector space V, we have a natural question. Can we turn V into a complex vector space? Or, more precisely, could we extend the real vector space structure on V to a complex vector space structure? Well, let's examine what we would need. Now, observe that defining a complex vector space structure on V is just equivalent to defining multiplication by I. And as a linear operator, multiplication by I is just an endomorphism satisfying the property that its square is equal to negative of the identity. So we see that if C is a complex vector space, then we must have an endomorphism I whose square is equal to minus identity. But conversely, if we have such an endomorphism, then we can use that to define multiplication by I on V and thus define a complex vector space structure on V. So this is if and only if. Thus, V has a complex vector space structure if and only if it has an endomorphism I whose square is equal to minus the identity. Now, it's kind of a mouthful to say an endomorphism I whose square is equal to minus the identity. So we'll give that a name. We'll call any such endomorphism an almost complex structure on V. And then from our previous discussion, we saw that if V is a complex vector space, then it has an almost complex structure, and vice versa. An almost complex structure on V induces a complex vector space structure on V. Now observe that an almost complex structure on V naturally extends to a complex linear map on the complexification of V. We'll also denote this map by I. In the next episode, we're gonna decompose this complexification into eigenspaces of I. And then we'll apply that to decomposing the complex tangent space.